what happens next? Okay, so let me show you a nice example of why we might want to use vectors to study parametric curves. Because after all, a lot of what's here you can just do in coordinates, and we don't really need vectors. Well, actually, vectors being a language, you never strictly need it, but it's useful to have a notion of vectors. So I want to tell you a bit about Kepler's second law of celestial mechanics. So that goes back to 1609. So that's not exactly recent news, okay? But still, I think it's a very interesting example of why you might want to use vector methods to analyze motions. So what happened back then is Kepler was trying to observe the motion of planets in the sky and trying to come up with general explanations of how they move. Before him, people were saying, well, they kind of move in a circle, but maybe it's more complicated than that. We need to add smaller circular motions on top of each other and so on. They had more and more complicated theories. And then Kepler came with these laws that said basically that planets move in an ellipse around the sun, and that they move in a very specific way along that ellipse. So there's actually 3 laws, but let me just tell you about the second one that has a very nice vector interpretation. So what Kepler's second law says is that the motion of planets is, first of all, they move in a plane, and second, the area swept out by the line from the sun to the planet is swept at constant time. Sorry, is swept at a constant rate. From the sun to the planet, area is swept out by the line at a constant rate. Okay. So that's an interesting law because it tells you, once you know what the orbit of a planet looks like, it tells you how fast it's going to move on that orbit. Okay, so let me explain again. So this law says, maybe the sun, let's put the sun here at the origin, and let's have a planet. Well, the planet orbits around the sun, in some trajectory. So this is supposed to be light blue. Can you see it as different from white? No. Okay. Me neither. Okay. Doesn't really matter. So the planet moves on its orbit, and if you wait for a certain time, then a bit later it will be here, then here, and so on. Then you can look at the amount of area, inside this triangular wedge. And the claim is that the amount of area in here is proportional to the time elapsed. So in particular, if a planet is closer to the sun, then it has to go faster. And if it's further away from the sun, then it has to go slower, so that the area remains proportional to time. So it's a very sophisticated prediction. And I think the way he came to it was really just by using a lot of observations and trying to measure what things were, what was true, what wasn't true. But let's try to see how we can understand that in terms of what we know today about mechanics. So, in fact, what happens is that Newton was quite a bit later. I mean, that was the late 17th century instead of beginning of the 17th century. So he was able to explain this using his laws for gravitational attraction. And you'll see that if we reformulate Kepler's law in terms of vectors, then, and if we work a bit with these vectors, we're going to end up with something that's actually completely obvious to us now. At the time, it was very far from obvious, but to us now, it's completely obvious. So let's try to see what does Kepler's law say in terms of vectors.